So which of these appliances speed up or slow down chemical reactions? So on the left we have a refrigerator, upper right we have a microwave oven, and down below that we have a stove. Now I think it's pretty easy to answer this question. The refrigerator is used to slow reactions down. And that's why we have low temperatures in the refrigerator. And the lower the temperature, the slower the reactions will go. Whereas a microwave and a stove are used to speed up chemical reactions. So that's the subject of this short video. It's going to be about kinetics. Now, kinetics is the study of reaction rates. There are various factors that affect how fast or slow a reaction goes. I'm going to go through those factors with you and give you some examples. Concentration. Usually, the more concentrated your reactants are, the faster the reaction will go. Temperature. Well, usually the higher the temperature, the faster the reaction will be. Pressure. Now, pressure really just affects gases. And so the greater the pressure, usually the greater the number of moles of gas, and the faster the reaction will be. Surface area is something that just affects solids. And if you increase the surface area of solids, you'll increase the contact, and therefore you should increase the reaction rate. Just think about dissolving a sugar cube in water versus dissolving a spoonful of sugar. The spoonful has a much greater surface area. And then we're going to take a look at catalyst. What is a catalyst and how does it do what it normally does? And that is to speed up a chemical reaction without itself being used up. We're going to take a look at the collision theory that helps to explain how all these factors can affect the rate of a reaction. And we're going to take a look at some potential energy diagrams. As I mentioned a moment ago, increasing these usually speeds up a reaction. Now for the catalyst though, usually a little bit of catalyst goes a long way. So let's take a look at the first example. So what I have here in A, I have a lighted splint. This is a little wood splint. I lit it on fire, and then it goes out kind of on its own. Now it still has some embers at the end here. So when wood splint is now placed into a bottle that contains oxygen gas, it bursts back into flame. What accounts for the difference in reactivity between A and B? Well, it's really the amount of oxygen. So in the air, we're subject to oxygen that's about 1/5 of the air pressure. Whereas inside of this bottle, it's just all oxygen. So there's a much greater concentration of oxygen in B than there is in A. Therefore, A is much slower than B. Now here's an example from a fire that happened in 2008 down in Savannah, Georgia. So this was a sugar refinery. And they wind up with a lot of sugar dust in the air. And it says sugar dust can be volatile, which means it'll evaporate quickly and then can explode. What happens with this is that you get this fine dust in the air. And if there's a spark at all, which can happen from somebody dropping a wrench on a metal, and hopefully they're not lighting a match in there at all, you provide the energy needed to start the reaction, because sugar can burn, whether it's in a cube or in a piece of toast or in dust in the air. And that dust in the air has a tremendous surface area. So once the reaction starts, it goes pretty quickly, and that's when we have an explosion. Now this happened in Massachusetts. So police waited an hour to shut down a road after reports of a natural gas leak in Somerset, Mass. that resulted in a fatal house explosion. According to a 9/11 emergency recording, Somerset Fire Chief Scott Jepson told NBC 10 there was not much that could have been done by firefighters or the gas company. They knew they had a leak. They were basically waiting for crews to dig up the road and shut it off. So in other words, they didn't know where the leak was going. We did readings in the house and didn't find any gas, or we would have evacuated. The problem is that under pressure, which the gas is, it'll migrate to any area where the pressure is less. And if that happens to account, let's say it encounters your cellar, it'll enter into a little crack. And once it does that, it can fill up the cellar and it will mix with air that's in the cellar. Now by itself, if you don't have too much gas coming in, not a problem. But as that fills up, it kind of creates a lot of pressure, and all you need is a spark to set it off. And that can happen either from a heater going on maybe, or somebody flipping a switch. So this kind of thing happens all the time. Up here, not that recently, but you hear about a house just exploding for no particular reason. It's always in the winter, and it's always because of the gas. Now let's take a look at the collision theory. What do we need to really have a successful collision? So here we have a diagram that shows in A an effective collision. Now what does that mean? So we have molecules traveling at each other, so they have a lot of kinetic energy, and now they crash in together, and then they form the products. So you notice that the products look different than the reactants do. Then in B, we have these same molecules going right at each other. It looks like they're going pretty fast. They collide together, but they just break off and are no different than before the reaction. So what's really going on? Well, you have to have a collision between molecules to have a reaction anyway. Just like if you don't have a collision between two cars, then you don't have an accident. But what does a collision need to be effective? Well, it needs two things. Number one, molecules must be traveling fast enough. They must have enough kinetic energy to overcome the repulsion that molecules have for each other. The second thing is they must collide at the right orientation. Now, if we look back at the diagram, you notice how they're hitting in these directions. The two molecules in blue here are hitting at these angles, whereas down here they're almost hitting on the same part of the red molecule. So this is why this is an ineffective collision. So even though there might be enough kinetic energy involved in the collision, if the angle is not correct, then nothing happens. Both conditions must be met for the reaction to occur. Now this is what we call a potential energy diagram. So let's take a close look at this. So we start from left to right, and this just says progress of the reaction. So we're starting up here with the reactants. And as the reactants are going towards each other with enough kinetic energy, the kinetic energy starts to be changed to potential energy. If we could see the reactants, they would look like they're slowing down. But it's almost like cars going up a hill. You know, if you take your foot off the gas, you can't go up the hill very far. The car starts to slow down. Yet the energy that was pushing the car up the hill is changed to potential energy. So the car could come riding back down the hill. So as the molecules are going towards each other, if they have enough kinetic energy involved in the reaction, they may collide together and form what we call an activated complex that you see written down here. Now, the activation energy is the minimum amount of energy required to start a chemical reaction. So if the molecules are not traveling fast enough, even if they do make it like halfway, they will simply go back to where they came and no reaction would happen. So the activation energy is the energy it needs to go from the bottom here to the top. If I had some numbers on the side, we could actually say what the activation energy was. So what happens now when we're up here at the top? Well, the molecules might either go back to where they came and reform, or they might go over here and start to form the products. And as they form the products, energy is released. Now, in this particular diagram, you notice that the activation energy is a lot smaller than the energy that's being released. And that's what we call an exothermic reaction, because the energy released is released to the surroundings. Now, what would you see? Well, you might see a flame, you might have an explosion. If this was in a test tube you're holding in your hand, you might just feel warm. Now, let's take a look at the opposite kind of a reaction. Here we have an endothermic reaction. So an endothermic reaction, the same thing must happen. First, the reactants must be going towards each other with enough kinetic energy, and they start to go up the hill as the kinetic energy is changed to potential. If we have enough energy involved in the reaction, we can form this activated complex, which is always right up here. And then as the molecules start to go down the hill to the right, they start to form the products. Now, in this case, if you notice, we wound up higher than we started. And that means that energy is being absorbed. And this would happen, this would like feel cold in your hand if it was happening there. So when we look at the reaction overall, we're taking the reactants which have less energy, they're down here, and they're making products of higher energy. So in an endothermic reaction, energy is absorbed from the surroundings, and the products you make are at higher potential energy. If we go back to the other diagram, for an exothermic reaction, you're starting with higher energy reactants and making low energy products. So this could be like, I could put in some for you here. Let's say we could have, for instance, CH4, methane gas, and we have oxygen gas. They could be your reactants. And when they finish reacting together, they produce, CO2 and water, which are our low energy products. And the difference in energy is released to the surroundings, which we want. This would also be the same as a reaction you did the other day with burning the magnesium. So potential energy diagrams are handy to try to show what's going on in a reaction. Now here they both are together, so you can compare them. So exothermic reactions always start up higher than they end, whereas endothermic reactions always start lower than they wind up ending. So how does a catalyst speed up a chemical reaction? Well, let's take a look at a diagram for that. So in purple here, we have the catalyzed reaction versus in blue, we have the uncatalyzed reaction. And what can we see? The activation energy for the uncatalyzed reaction is a lot higher. The activation energy for the catalyzed reaction is a lot lower. So therefore, you don't need as much energy to start the reaction if you use a catalyst. You still need energy to start it. You're not wiping out the energy requirements at all. But remember, we have hundreds of chemical reactions happening within us every minute. And those chemical reactions, even though they do employ catalysts, that's what enzymes are. They employ catalysts, but they only run at certain temperatures. That's why our body temperature for us would be high. It's all like high 90s. If the temperature drops down from that too much, then you won't have enough energy even for a catalyzed reaction. So just in summary now, factors that can increase the reaction rate: more reactants, or the greater concentration, the more collisions you're going to have, and the greater the chance for successful collisions. Higher temperature, more collisions because you're providing the activation energy. Adding a catalyst can lower the activation energy and thus make the reactions go faster as well. All right, so that's just a little summary of the field of kinetics.